So this question asks you to look at this rational expression, and when we say rational expression, we mean one polynomial divided by another polynomial, so that's what we see when we look over here, v minus 6 over v squared minus 81. And the question asks you to find all excluded values for this expression. And helpfully, so this problem expands on that thought, but on the exam and on your quizzes it tends to stop there. But it expands on it here to remind you what excluded values mean. What we're looking for is to find the values of v, which is our variable here, for which this rational expression is undefined. And so I have to ask you, what makes an expression undefined? What does that even mean, and how are we going to know it when we see it? The value of this rational expression depends generally on the value that we plug in for its variable. If I plug in an 8, it's going to spit out negative 2 over 17. So going back to the question asks, when is this expression undefined? And undefined means not that the value of the expression is 0, but that the value for the expression isn't even a number. Isn't even a number at all, which is weird, right? This means that conceivably there could be a number that I plug in for v in this expression that makes this whole expression fail to be a number in any way, shape, or form. So how is that even possible? How is it possible to put in a number into this expression to break this expression, to take away its numberness? What happens? Let's start by factoring everything we see. Always a good idea when you first meet a brand new rational expression. Try to factor it to the extent that's possible, because the factors will help us to best understand what's going on here. Well, there's nothing to do upstairs. V minus 6 is already completely factored, as much as we can do. But what about v squared minus 81? How does v squared minus 81 factor? Yeah. So if we look at this, because 81 is a perfect square, I can write negative 81 as a 9 and a 9, one of which is negative. And my v squared I can write as a v and a v. And in doing so, we'll find that the cross terms, the middle terms, will cancel one another out, as they do in a factorization of a difference of two squares. So we can factor this denominator as v plus 9, v minus 9. So now we understand this rational expression in a new way, in a better way. Right? It helps us better understand what pieces make up the numerator and the denominator. So now we can go back again to the question, what is it that's going to make this fraction undefined, make it fail to even be a number anymore? What can happen? The one and only one way to make a fraction fail to be defined is to make its denominator 0. The one number that we don't know how to divide by is 0. And in fact, in arithmetic, it's the only arithmetic operation that fails to yield an answer. We can add 0, we can subtract 0, we can multiply by 0, we can add, subtract, multiply any number, we can divide by any number in the world that we want to and get an answer, except we cannot divide by 0. And so, if we want to know which values this expression is undefined for, that's synonymous with the values for which the denominator becomes 0. And that's the key. It's the one thing in arithmetic that we cannot do is divide by 0. So how do we find those values? Yeah, we're just going to take that denominator and say, well, how am I going to know when this denominator is equal to 0? And because we've already factored the denominator, we're most of the way there. Because we have a 0 on the right-hand side of this equation and the left-hand side is factored, we can split the two factors apart. And when I split them apart, each one of my factors gets its own 0 on the other side of the equal sign. And all I have to do then is solve each one of those two equations separately. If v plus 9 is equal to 0, what does that make v? Negative 9, subtracting 9 from both sides. And if v minus 9 is equal to 0, then v is positive 9. So tracing all of this logic backwards, If either v is negative 9 or v is positive 9, then that's going to mean that either the factor v plus 9 or the factor v minus 9 becomes 0. And as soon as one of those factors becomes 0, the whole denominator of this fraction becomes 0. And when the denominator of a fraction is equal to 0, that fraction does not have a defined value. You can try it on your calculator. Try plugging in 10 divided by 0, enter. It'll give you an error. It'll do something that indicates that you've broken the calculator, right? You have to move on. So finding excluded values for an expression is synonymous with finding those values that make its denominator equal to 0. Factoring helps. It definitely helps in this process because that's our favorite tool and heretofore our only tool for solving to find out when a polynomial is equal to 0. We're going to develop one more tool in Module 10. I want also to connect this idea of excluded values with an idea that you're going to meet in pre-calculus when you see particularly rational expressions come back to you next semester in pre-calc. One of the most powerful tools that we have for understanding algebraic expressions is to understand their graphs. So if I were to graph this expression, I'm going to replace the v's with x's instead. So x minus 6 over x squared minus 81. If I were to graph it, I would be looking at those points for which the value of y at that point is equal to the value of x minus 6 divided by the value of x squared minus 81. So if I were to graph this, it should give me an indication of the properties of this rational expression. So I made a quick graph in a platform called Desmos Graphing Calculator. This is a free graphing calculator. Here's what that graph looks like. So it's not a straight line like the graphs that we met in Module 4, right? It's curvy because the form of the equation doesn't follow y equals mx plus b, right? There's a lot more going on. The numerator looks like it's mx plus b, but then it's divided by something else that's giving it very different behavior. So now my question is, based on the work that we did a minute ago, we found the excluded values of this rational expression were, respectively, negative 9 and positive 9. My question to you is, how is this graph telling us that story? What do you think? If I were to ask you on this graph, where is there a point on this graph, on the red graph, that has an x-coordinate of negative 9? What would you say? I'd be coming over here to negative 9 on the x-axis and looking for a point on my graph that has an x-coordinate of negative 9. But if I look above negative 9, I don't see any point. It looks like this graph kind of gets really close to that line, but it never actually has a point where that line and the graph share the same space. So there's no point on the graph above negative 9 x value. There's also no point on our graph that's below negative 9 for an x value. So what we might say is that no point on this graph has an x-coordinate of negative 9. And the same is true with positive 9 also. That if we go up to x equals positive 9, which is right here, and we look above positive 9 and we look below positive 9, the story is the same. Below x equals positive 9, there's no point on the red graph. It gets really, really, really close, but it never actually gets to a point where x is equal to 9. And likewise on the right-hand side of it. It gets really, really, really close, but then there's never actually a point. I'm a little bit off in my sketch here. There's never actually a point that has an x-coordinate of 9. So both of these values are problematic with respect to the graph. So it's true for negative 9. It's also equal to positive 9. And in pre-calculus, you're going to call these vertical lines vertical asymptotes. Not a word that we use in our course because we don't deal as much in graphs as you will when you take pre-calculus. But a vertical asymptote is this feature of a graph that can only happen at excluded values of the expression which defines that graph. So the reason that vertical asymptotes exist for this function, for this equation, y equals x minus 6 over x squared minus 81, the reason these asymptotes exist is because at those x values, that expression fails to exist at all. And so there's no point on this graph that has an x-coordinate of plus or minus 9 and has a y-coordinate which is actually a number. And so we see this bizarre behavior. Our graphs are breaking at that point.